I'm John Mather. I'm Senior Project Scientist for the James Webb Space Telescope, now in preparation for launch in December 2021. And we've been working on this since 1995. I want to show you something of the history of the universe and how the Webb telescope will help us find out more about it. But before that, I want to show you something of my own history. This is the place where I grew up. This is Rutgers University Luscroft Farm. It's in far northern New Jersey, a place where people did research on dairy cattle to get more and better milk. For me, it was a wonderful place to look at the sky and to learn science from books and from playing around in the basement of our house with tools and with lenses and mirrors and things to make telescopes. But I couldn't become an astronomer just yet. So went to school and did all those things that people did in school. But in the back of my mind all this time have been these kinds of questions. How did we get here? When I was a school child, people had no idea. Well, maybe I should say we had lots of wrong ideas. Now we know the universe is expanding from a very smooth and very hot early times. It has been unstable in thousands of different ways, and basically energy has been released as the universe reorganizes itself into complex systems, and particularly releases gravitational energy to heat up things and let them become stars and galaxies. The universe is extremely large, probably infinite, which is to say without any boundary, and it's very, very old, about 14 billion years almost, and it's big enough and old enough that even things that seem very unlikely and very rare to us have had time to become reality. So in particular, what seems mysterious to us is the possibility that we ourselves exist. So how did we get here? So we're beginning to learn some of the process. We've learned about stored information. DNA was recognized in 1953 to be a digital code stored in a double helix molecule that every cell uses to keep track of what it should do next. And the cells have their little secret decoder rings that read the DNA molecules and issue commands to the rest of the cell so that it can do what it needs to do. There are other kinds of stored information, such as our own languages, that enable us to talk with each other, to remember from generation to generation all of the discoveries of our ancestors. And these bits of stored information also control the evolution of life, which I call survival of the lucky, because there's no particular guarantee that our life form is the best or the most suited to our environment, but we have been lucky enough to be here as people looking more or less like ourselves for several 100,000 years. So it's still a great mystery how this works, but we know it does work. We've also been learning about feedback loops in control systems, and the living things that we're made of. The cells have their own, and they've made it possible for me to have my own identity, even though most of my cells and most of my atoms have been replaced over and over again throughout my own life. So it's a great mystery, but scientists are working on it. And so one of the questions we have and have always had is our life form especially rare, or even almost impossible to find, or is it likely that it is a commonplace result that occurs wherever the conditions might be suitable for life? So scientists have no idea how to calculate this. We have had many people who thought they could calculate it, but honestly, we do not know. Do not know how it would work, do not know where it would happen, but we do know from the one observed data point here on Earth that life left fossils in the bottoms of the ocean shortly after oceans appeared. So within a few 100 million years after oceans, we have fossil life. Then it took another 2 billion years for complex life to occur, and then almost another 1.5 billion years for creatures with eyes and legs to appear. So our particular form of complex life with the civilization that we have has taken the entire history of the universe for us to appear. So could there be other life? Well, of course. We have no idea, we have no measurements, but we have to go look. That's part of our challenge as scientists and as NASA astronomers. So we should look at the places in the solar system, and we should look at other solar systems. So, history of the universe. In 1929, Edwin Hubble showed that distant galaxies are going away from us with immense speeds that are about proportional to the distance. if you divide the distance by the speed of motion of each one, you get an apparent age of the universe. And he got the wrong answer, but he did show that the universe does seem to be expanding, and we still think that. So we found his mistake, and now we know the age of the universe. The distance divided by the speed is about 14 billion years. So that's a wonderful and wild story, and it was almost completely unexpected by Einstein and all other astronomers except for two. The big story there. So how are we going to know about this? Well, many ways. We look with the Hubble telescope, we take pictures, and we also built this apparatus, which was the Cosmic Background Explorer satellite, which I had the pleasure of being the scientific leader of, and it was launched in 1989. By the way, it was based on my own thesis project at UC Berkeley, and it failed as a thesis project, but real engineers made this one work in space. We measured the Big Bang. We showed that it is hot and that it has the right temperature and spectrum. It has hot and cold spots to explain our own existence. So it was a huge triumph, and that was a project that earned a Nobel Prize for the team and especially for me. So coming after that, well, what are we going to do to know more? Well, we built the Hubble Space Telescope, and we took marvelous pictures, and they're beautiful, and they confirm the story. And then astronomers said, well, that's beautiful, and we still can't see everything we need to see. And they wrote a little book, and they said, please build us a more powerful telescope, which we now call the James Webb Space Telescope. We are leading this project at NASA Goddard Space Flight Center, where I am, and we're doing it in partnership with the European and Canadian space agencies. Our major contractor is Northrop Grumman Space Systems, and we have pieces from all around the world, that is to say, from the United States, Canada, and Europe. And we will be operating this observatory from the ground, as we do the Hubble Space Telescope, by commanding it from the Space Telescope Science Institute in Baltimore. So this telescope that you see in the picture is very different from all other telescopes we've ever built and flown. That big golden hexagon that you see in the middle is 6.5 meters across, about 21 feet. And it collects the starlight and the galaxy light and focuses it into the instrument package. It is so much more powerful than the Hubble telescope that it's hard to even calculate how much more powerful. But the main thing that it has that's different is it's cooled down to a very low temperature, cold enough so that it itself does not glow, does not send out infrared light. That means that it can pick up the infrared light from the most distant universe, from the stars and planets being born today. It can even see inside dusty clouds of gas where stars are being born. So all of these things make it very different and special, as well as more powerful than the Hubble Space Telescope. Now, of course, to get this great telescope to be so large, it has to be folded up to be able to be launched from the ground in a single rocket. It will be unfolded after launch. That big blue piece that you see in the picture is actually a big umbrella of 5 layers of very thin plastic. They're metallized to keep the heat from the sun from getting to the telescope. So that blue sunshade is about as big as a tennis court. It's a totally astonishing feat to be able to fold that up, the whole telescope and the whole sunshade, to fit in the top of the rocket. So what are we going to see with it? We are going to look at everything that we know of already, and we think that we will see back to the epoch of the very first galaxies being born from the Big Bang material, whatever that was. We have good reason to think from the Hubble Space Telescope that we know what they ought to look like. So this is a Hubble telescope picture, and what we should see that we don't see in this picture is little tiny red specks, or I should say infrared specks, that are too faint and too red for the Hubble telescope to be able to pick them up. So that's one of our great intentions and difficult challenges, is to see those very first ones that grew from the Big Bang material. We think they'll be different from the galaxies we see today, and that's part of our own history that's really interesting and fascinating for us. Almost everybody seems to say, well, where did I come from? And astronomers are working on that part of the puzzle. What is the history of the atoms from the early universe? How did they get into stars and galaxies and eventually planets and people? So we're working on that. And so the galaxies are the first things to form. Then we look inside clouds nearby to see how are the stars being born. This is a place called the Eagle Nebula, and it's a beautiful picture. As you see on the left side, that's a picture taken with the Hubble Space Telescope. You see these wonderful blue glowing clouds of gas, and the dark sections that are dirt in space, dust in space, that stop the starlight from coming to us. And if we say, well, let's move to infrared wavelengths, that is to say a little bit longer wavelengths than you can see with your eye, then you get the picture that we see on the right. So the infrared is able to go through the dust clouds a little bit better. We begin to see inside, and we see a completely different picture. Astronomers will say, if we can go to much longer infrared wavelengths, we can see right inside and see the stars being born in that cloud, and maybe even signs of planets being born with them. So we'll certainly be looking at places like this. We will be looking in our own solar system as well. We know there's some fascinating places to go, and we are actually planning to send probes to these two places. Europa is a satellite of Jupiter. It's shown on the left, and we have a picture taken by our Galileo mission when it went to visit many years ago. And you see a surface that's more or less white and is covered with cracks. The cracks are places where the ice has allowed brown material to come up from underneath in the ocean underneath and come out. So astronomers saw this and they said, well, an ocean, that's a good place for life. Let's go look. Recently, we've gotten fortunate and we discovered that some of that water comes spitting out of the satellite of Jupiter in little geysers, and we are aiming to send a probe to fly right through the water spouts and pick up samples of the atoms and molecules coming up to see if there's any sign that that water underneath was alive. On the right-hand side, we show you a geological map of Titan. Titan is a satellite of Saturn. It is a satellite that has a very thick atmosphere of nitrogen mostly, also some hydrocarbons, and it has lakes and rivers and rocks and craters and dunes, and we're sending our probe over there to find out. If we wanted to know if life is possible in some other way besides the kind that we have here, this is the first place to go look. You could tell if a hydrocarbon solvent, that is to say liquid methane and ethane, could be the basis for life, then this is definitely the place to go look, because nature has been doing this for billions of years. So we'll send a helicopter over there to go hopping around and look for evidence of interesting things in preparation for even more serious missions that could look for real signs of physical life. So what do we do in addition to that? We go out and look at planets around other stars. Now here is a way that we do that. We wait, for instance, for a planet to go in front of a star. This doesn't happen all the time. It only happens for a short part of the orbit of some planets around some stars. Nevertheless, there are enough that we can do this trick, so you can begin to analyze those planets orbiting around other stars and even study the molecules in the atmospheres of those planets, because some of the starlight goes through the atmosphere of the planet on its way to our telescope, and we can analyze all of that and look for signs of water and anything else that might be interesting in those spectra that we get from those little planets. Small planets, big planets, there's quite a large catalog of targets of this sort. We hope to have some interesting surprises. So to come to the end of my talk, I want to talk a little bit about why I do this and what it takes to become a scientist, to be a scientist. I think the first perspective is I'm interested in what I don't know and what nobody knows. So we're very curious as scientists, and I think children are very curious. I think adults can be very curious when they're not too busy being worried. So my strategy is, well, I've got to go look. I've got to go measure something, because I can't actually think about the way things are as well as nature does. So we have to go measure, have to go look. So another point here is that although people might like to think that we have effect on that football as it flies through the air towards the goalpost, my actual opinions do not affect anything. They do not affect footballs. They do not tell us what's really out there. So we have to go look. In school, I learned about something called Occam's razor, which is a principle that says we should have the simplest possible explanations. However, nature tries everything, and nature is clearly not simple. Nature is only very complex. So nature's complexity is something that means scientists are never going to run out of things to do. A corollary of that is if something can happen, it will. If something can go wrong, it will. So many names for that principle. Another thing about being a scientist is it's really great to tell people about what you're thinking. You can get very good at that, and it is a secret skill for scientists to have a good time being scientists. So to wrap up, people often want to know, how far can we go? Well, robots can go anywhere. On the Earth, under the Earth, in the water. They've been already to visit all of the planets, some dwarf planets, interesting asteroids, comets, moons, everything. We've even managed to bring back some samples from other objects already, and we are currently collecting samples on Mars to bring them home from there with robots. So that's working. We're very proud of that accomplishment. And computers are obviously getting very much smarter every year. Now that's a tricky thing. You can imagine some year that they'll be smarter than we are, and who knows? Plenty of people will tell us that that's not possible, but I don't think that's impossible. On the other hand, we do know that people ourselves are extremely fragile. We do not like vacuum. We do not like getting bombarded by cosmic rays, and we can die on our trip to Mars if we are unlucky. So ideally, we should have better engineering to be able to go much faster. In the long term, think about robots. All those things you see on the television and science fiction stories, no, those are not likely to happen because space is just extremely large, and the nearest places outside the solar system that somebody else like us could be living are so incredibly far away that it would take hundreds of thousands of years or more for them to get here or for us to get there. Nevertheless, a robot could go if it feels like it, if it wants to, or if its owners want it to. But they will still have to be very patient, because when they get where they're going and they send a message home, the world will have changed. It's a wonderful challenge. At any rate, we people are in a remarkable position to make this happen.